This is the 8th video in our series on topology, and today we're going to talk about the metric topology. This will probably spill over into the next video as well, but we're at least going to get started with the metric topology. But in order to know what this topology is, we need to know what a metric on a set is. So a metric D on a set X is a function which takes in 2 points from X and gives us a real number. And the way you want to think about this is that this is like a ruler that's measuring the distance between those 2 points in X. And so if this is a ruler measuring distance, then that means that this function should really satisfy some conditions which are maybe obviously satisfied by a good notion of distance. First of all, the distance between a point and itself should be equal to 0. I think we can all agree upon that. And then next, the distance should always be positive if you look at two unequal points. That's what we have here. And then the distance shouldn't matter if you measure from one point to another point or vice versa. So in other words, d of xy must be d of yx. We've got some symmetry. And then finally, there should be some sort of triangle inequality. And so if you measure the distance straight from x to z, that should be less than or equal to first measuring the distance to y and then measuring the distance to z. And that's exhibited by this inequality right here. So let's look at some basic definitions of metrics before we really dive into the results. And so let's say we've got a function d from Rn cross Rn to R. And what it does is it takes the norm of the vector x minus y. And well, what do I really mean by norm? Well, you take the dot product of x minus y with itself, and then you take the square root. And so you're probably familiar with this kind of thing from a linear algebra class. Well, it turns out that that is a metric. And this is actually true for any so-called normed vector space. But we really mostly want to look at small values of n here. So if n is equal to 1, then the distance function is simply, well, the absolute value of the difference. I think that's a fairly maybe obvious distance to take. And then if we've got n equals 2, the distance, well, that's just the distance formula that you learned probably in your first geometry class. And you can build this distance formula by, well, what are you going to do? You're going to use the Pythagorean theorem on the points x1, y1, and x2, y2. I'll let you think about how to derive that. And I guess we're not checking these axioms over here, but they should be fairly clear. Maybe it would be a good exercise to check the triangle axiom on this x minus y if you're interested. And so, well, there are other metrics other than these. Every metric that's built like this is the so-called Euclidean metric. There's this thing called the taxicab metric. And what that does is, well, looking up here, it essentially distributes the square root onto all pieces of that sum. But if you take the square root of a square, you get the absolute value. And so that's what we have here. It's the sum of the absolute value of x1 minus y1, and then the absolute value of x2 minus y2, all the way up to xn minus yn. And why is this called the taxicab metric? Well, think about our point right here, x1, y1, and x2, y2, as being places in a city. And the roads only run in this direction and then this direction. Well, then the only way to get from this point to this point is by following a road horizontally and then vertically. But then this point right here will be, well, I guess my variables are a little off. I think this is the natural way to write it generally, but this will be kind of this object right here, and then the distance right here will be the other one. So in this case, we're getting absolute value of x1 minus x2 and then y1 minus y2. But like I said, generally it's a little bit better to write it like this. In this specific R2 case, it's nice to take advantage of the xy plane. And then, well, there's this thing called the Chebyshev metric, which just looks at all of those absolute values and then pulls out the maximum one. And in fact, that's a metric as well. Now, maybe we'll check the triangle axiom for this one and then perhaps the Chebyshev metric as well. Okay, so let's look at the distance from x to z. So notice that that's going to be the absolute value of x1 minus z1, and then plus the absolute value of x2 minus z2. But now we can apply the triangle inequality to both pieces of this, keeping in mind that the triangle inequality will hold for our distance formula up here, or yeah, our metric up here. So this is going to be less than or equal to the absolute value of x1 minus y1 plus the absolute value of y1 minus z1, and then plus the absolute value of x2 minus y2, and then plus the absolute value of y2 minus z2. So just to be clear, this is spreading out into these two terms by the triangle inequality on the absolute value function, and then the second term is spreading out into the third and the fourth terms. Okay, and then from there you can put these two things back together. So these things that I'm underlining in blue, well, that's going to be equal to the distance between x and y. And then likewise, the stuff that I'm underlining in red, that's going to be the distance between y and z. But that's what we need for that triangle inequality to hold. And then, well, we can do kind of the same thing here. We can actually do it in general. So let's do the distance between x and z. So that's going to be the maximum of all of these xi minus zi. But then that's going to be less than or equal to the maximum of all of these xi minus yi, and then plus yi minus zi. And that's just by applying the triangle inequality to each of the things in there. And then I guess there's a little bit that you need to do to be able to split this maximum function up linearly, but this will be less than or equal to the maximum of each of those individually. Again, we're kind of playing it fast and loose here, but if you want to check the details, I urge you to. And what you'll end up with is, over here, the distance from x to y plus the distance from y to z as needed. All right, so hand in hand with the notion of a metric, especially if we're working towards the metric topology, we'll need to know the notion of an open ball. So we'll define the open ball centered at a point A in X with a positive radius R to be, well, essentially all points that are within R units of A. So we could write that out as, well, our notation is B sub R of A. We've got all x in x so that the distance from A to x is less than R. So let's look at some examples. So let's say we take R with the Euclidean topology. So if we go over here to some arbitrary point, and then what we'll do is simply go R units to the right, and then R units to the left, and make an open interval. So this is going to be our open ball. So I guess we could pretty easily write that as the open interval A minus R to A plus R. Now in the Euclidean metric, we'll really see why it's called an open ball, and that's because, well, you're going to get something that might be called an open disk. So if we go here to A, and let's say that this is a distance R, then what we want to do is put a circle of radius R centered at A. And then what the ball will be is simply all of the points inside of that. So that's going to be the open disk in this case. And of course, in 3 dimensions, you would get, well, exactly an open ball. Now let's look at the taxicab metric. So let's go over here to our point A. And notice that something straight to the right of it, which might have coordinates A1 plus R and A2, that'll be just on the edge. And then maybe something above it, which would have coordinates A1, A2 plus R, will also be just on the edge. And then there'll be maybe the cousins of those over to the left and to the bottom. So we have something like this. But then let's also note that by the taxicab metric, the point right here, which has coordinates A1 plus R over 2 and A2 plus R over 2, also has a distance of R from our central point A. And we can see that because, well, we're going to go r over 2 units vertically and then r over 2 units horizontally. So now putting this all together and kind of extrapolating what we're seeing, the open ball in this case will be like this open square on its side. Maybe we'd call that an open diamond. So again, that's kind of the idea of a circle or a disk in the taxicab metric. So now let's look at the Chebyshev or the maximum metric. So let's go over here to just an arbitrary point A and observe that the point right here, maybe we'll put it like this, which is A1 plus R, A2, that's going to be a distance R from A pretty clearly because the maximum of the distance of the two components is most definitely R. But now notice that if we go up here to this corner, and this point is A1 plus R and then A2 plus R, notice that the distance from each component to the center point is R. But if we take the maximum, we get R. And then, well, you can extrapolate out, and now we're going to get a square, which is maybe not on its side. And I guess we should have dotted lines along the edge of the square. So in this case, in the Chebyshev metric, notice that an open disk is this type of square. Okay, so our next proposition will bring in this notion of the metric topology. So let's say we've got a set X and then we've got a metric D. We'll say that that's a metric space X comma D. Then the set B, which is the set of all open balls formed out of elements of X, is a basis for a topology on X. And that topology is known as the metric topology. So if you recall from the definition of a topology, there are two things to check. First of all is that every element of X is inside of an element from the basis or the would-be basis. And in this case, it's fairly easy because notice that for all A in X, and actually if we take all R bigger than or equal to 0, we see that A is most definitely inside of the ball of radius A centered at R. Sorry, the ball of radius R centered at A. But this ball of radius R centered at A is within this set that we want to be a basis. So we're good to go there. Everything is in one of these basis sets. Okay, and then let's also recall that there's some sort of intersection condition on the basis elements. So let's suppose that we've got a point A and it's inside of the ball of radius R1 centered at A1 and the ball of radius R2 centered at A2. Now, we might want to make a picture of what's going on here. So I'm just going to draw a circle here for our balls. So let's say this is the point A1, and then let's say we've got another ball over here, and let's say this is the point A2. So what we have is our point A is right here. And so notice that this distance right here is going to be less than R1, and this distance right here is going to be less than R2. But what we want to be able to do is squeeze another ball inside of this intersection. And there's actually, in fact, a way to do that, and we can do that by what the measurement would look like in the Euclidean metric, and the same type of measurement will work in this maybe arbitrary metric as well. Okay, so let's set D1 equal to the distance from A1 to A. So that's the distance from A1 to A, so that's like from this point to this point. And then let's set D2 equal to the distance from A2 to A. So that would be like from here to here. Okay. And notice that both of these are, well, less than or equal to Ri, depending on the I. So this is less than or equal to R1. I should say strictly less than R1 and strictly less than R2. Okay, so next up what we'll do is set delta equal to the minimum of R1 minus D1 and then R2 minus D2. So let's see, what is R1 minus D1? Well, that's going to be the distance from A to the edge of this circle. So R1 minus D1 is the distance from A to the edge of this maybe upper left circle. And then R2 minus D2 is the distance between A and then this other circle. So we're taking the minimum of those. But if we take the minimum of those, then the ball centered at A of radius delta will be completely contained in both of those circles and thus inside of the intersection. So then kind of by construction, what we have is A is inside of the ball of radius delta centered at A, which is a subset of the ball of radius R1 centered at A1, intersected with the ball of radius R2 centered at A2. I guess we should probably check that this set is contained in this set and that this set is contained in this set. But in fact, we kind of did that already in a specific case earlier, but maybe let's sketch out why this works. So let's take an X inside of the ball of radius D centered at A. But observe, that means that the distance from A to X is less than delta. I think I said D, but I meant delta. But notice that delta is going to be less than or equal to R1 minus D1 and R2 minus D2. But let's first use the fact that it's less than or equal to R1 minus D1. But that tells us that the distance from A to X plus D1, just moving the D1 over. So what's D1? That's the distance from A to A1 is going to be less than or equal to R1. I guess strictly less than because we've got this strict thing right here. But now we can apply the triangle inequality in this direction to have the distance between X and A1 on this side. So check it out. We've got the distance between X and A1 is strictly less than R1. But we could have done the same thing for R2 as well. And in fact, we can do them both at the same time just by putting an I here. And since we've got an I there, that's going to be true for I equal 1 and 2 by construction. But this means that X is inside of the ball of radius R1 centered at A1 and X is inside of the ball of radius R2 centered at A2. But then that proves this subset relationship right here, which is, where we needed to go. Okay, so let's see what we can do with all of this. Okay, so now let's prove that if we've got a set with the metric topology, then U in X is open if and only if for all of the points A inside of this U, there exists a delta bigger than 0 such that the ball of radius A the ball of radius delta centered at A is contained in U. So here's a picture of this. So let's say that this wiggly thing here is our set U. And let's take an arbitrary point A inside of U and observe that we can hopefully find some sort of delta where the ball of radius delta centered at A, so that would be like that kind of picture right there, is totally contained inside of U. So that's the idea of what's going on here. So this is an if and only if statement. Let's prove the forward direction first. So let's start by supposing that U is open, and let's say that we've got a point A inside of U. But now, since open balls form a basis, then that means that there is a basis ball, if you will, that is containing A inside of U. But that basis ball may not be centered at A. That's the important thing. But let's bring all of that into existence. So that means there exists a B inside of X and an R bigger than or is equal to 0 such that A is inside of the ball of radius R centered at B, which is totally contained inside of U. So again, this is based off the fact that the open balls form a basis for the metric topology. Okay, so now here's what we'll do from there. So it just is a pretty straightforward calculation, and what we'll see is that we have A is most definitely going to be inside of the ball of radius r minus the distance between A and B centered at A. Well, notice that the A is inside of the ball of radius anything centered at A. That's not surprising. But then this is going to be a subset of the ball of radius r centered at B, which is in turn a subset of U. Now, maybe this subset relationship from here to here you might want to check, but you'll use the triangle inequality. It'll be pretty similar to what we did before. But check it out. Is that what we needed? Yes, we've got A is inside of this ball of radius something centered at A, which is a subset of U. But check it out. We just found the existence of our delta. Our delta is this r minus distance from A to B. Okay, so now let's look at the reverse direction. But I claim that the reverse direction is fairly clear because let's recall that U is open if and only if for all A in U there exists a set B from the basis for the topology such that A is in B, which is a subset of U. That's something we proved quite a bit earlier when we talked about the basis for a topology. And now we can just run this in reverse to start here and show that U is open. Okay, so next up we want to show that if we've got a metric space with the metric topology, then with that topology, the space is necessarily Housedorf. Now let's recall that something's Housedorf if you take any two unequal points in the space, you can find neighborhoods of each of those points. Well, I'll call them U sub A and U sub B, such that A is in U sub A, B is in U sub B, and U sub A intersected with U sub B is empty. So this is like somewhat of a separation axiom, if you will. You can separate points into non-intersecting open sets. So now what we want to do is construct these types of neighborhoods using the metric topology. Okay, so how can we do that? Well, let's draw a little bit of a picture. Let's say that this is our point A, and then let's say that this over here is our point B. Now, let's find something exactly between them, and then let's draw a circle around A with that radius. And then let's also draw a circle of radius around B with that radius. And observe that if these are open disks, or if we shade them in like they're open disks, then these open disks do not intersect. Now, if you're a little bit worried about them almost intersecting, we could just like cut the radius by half or something, but we don't really need to do that. So let's set D equal to the distance from A to B. A is inside of the ball of radius D over 2 centered at A. B is inside of the ball of radius D over 2 centered at B. And we claim that the ball of radius D over 2 centered at A intersected with the ball of radius D over 2 centered at B is empty. And then, well, if we can do this, then we've shown that we do have a Housedorf space in this case. And we can do this kind of by way of contradiction. So let's say we've got an X inside of this intersection. So then let's look at the distance from A to B in this case. So using the triangle inequality, we know the distance from A to B is less than or equal to the distance from A to X plus the distance from B to X. But then given that X is in the ball of radius D over 2 centered at A, we know that's strictly less than D over 2. And then the other distance is also strictly less than D over 2. But then if you add those two together, you get D, which is the distance from A to B. But that's problematic because we have the distance from A to B is strictly less than the distance from A to B, which is of course something that can't happen. Meaning that we really don't have a point inside of this intersection, and thus the intersection is empty, and thus we have a Housedorf space. Okay, so now we're going to finish off with a definition, a nice example, and then some exercises. Okay, so the definition we want to kind of end our definitions with today is the idea of metrizability. So let's say we've got a space X with a topology T, and then we'll say that this is metrizable if there's a metric on X, so that the metric topology built out of that metric is the same as the topology T. And now this is super important because you can put a lot of different topologies on, for instance, the real numbers, but not all of them are metrizable. So in other words, some of them don't allow you to build them out of a metric, if you will. Okay, so we'll look at some more of that a little bit later, but what I'd like to end with today is this nice example. I think this is a classic example. So let's say we've got any metric d on a set X. Now we want to show that this thing, which we'll call d tilde, which is the original distance over 1 plus the original distance, is also a metric. Now I'd like to observe quickly that, notice that d tilde, well, it's always going to be bigger than or equal to 0, just based off of what we have here. Notice that this is bigger than or equal to 0, and this is also bigger than or equal to 0. But it's always less than 1, and that's because the denominator here is always bigger than the numerator. Now there are 3 things to check for a metric. Notice that 2 of these are pretty boring. This first one is fairly obvious just by the fact that we originally have a metric. The second one is also obvious by the fact that we also have a metric. So really what we'll check is just this third one, this triangle axiom. So let's set f of x equal to the function x over 1 plus x. This will be useful here. And let's consider this as just a function from 0 to infinity. So just a function on the non-negative real numbers. And now let's quickly note why we're looking at this function in the first place. And, well, observe that our new thing that we want to show as a metric, d tilde of ab, is simply f evaluated our old metric ab. Okay, cool. Now I'd like to do a bit of a calculation, so I'll let you check this, but if you do f prime of x, you get 1 over 1 plus x quantity squared. But observe that this is bigger than 0 for all x on the interval that we're interested in. But that means that f is increasing. So it's an increasing function. So let's just keep that in mind. And then also, I'd like to apply a theorem from a Calculus 1 type class, the mean value theorem, to this interval a to a plus b, with b bigger than or equal to a. Okay, so let's see what that's going to give us. So that tells us that there exists a c on the corresponding open interval such that f of a plus b minus f of a over a plus b minus a, which is b, is equal to f prime of c. Remember, the mean value theorem says that the average rate of change is equal to the instantaneous rate of change at a special point, which is equal to, by our previous calculation, 1 over 1 plus c squared, which is less than or equal to 1 over 1 plus c, simply by the fact that we're squaring something bigger than 1 or bigger than or equal to 1 in the denominator. Okay, so now let's observe that that means that f of a plus b minus f of a is going to be less than or equal to b over 1 plus c. But now let's observe that c is bigger than a, but then a is bigger than or equal to b. So if we replace c with b, then we push that bigger even still. So this is less than or equal to b over 1 plus b, which is equal to f of b. But notice that we can move things around here, and we'll see that f of a plus b is less than or equal to f of a plus f of b. And now we're ready to finish off this calculation. Notice that we have the distance from maybe x to z, is going to be equal to f evaluated at the original distance from x to z, which is less than or equal to f evaluated at the original distance from x to y plus the original distance from y to z. I'm able to make that change because our function is increasing, so I replaced the argument with something bigger. I got something bigger in the end. But now I can apply the inequality I just built to have this is less than or equal to f evaluated at this distance plus f evaluated at that distance, but that's just our d tilde. So we have d tilde evaluated at xy plus d tilde evaluated at yz as needed for the triangle inequality to be satisfied. All right, so now let's end with some exercises. Okay, so here's some exercises. So let's just say we've got the normal Euclidean metric on R2, and then we define this metric d tilde as in the previous example. Now, we know that's a metric from the previous example. Let's sketch the following three sets. So this is the ball of radius 1/4 centered at the origin, the ball of radius 2 centered at the origin, and finally the ball of radius 1/3 centered at the point 1, 2. Okay, so next up, let's say that we've got a metric space XD, and let's say that T is the metric topology. Then let's define a new function, d hat of xy, to be the minimum of 1 and dxy. So let's show that d hat is a metric, and let's say that t hat is the corresponding topology built out of this metric. And then what we really want to show is that t and t hat are the same topology. So in other words, U is an element of t if and only if U is an element of t hat. That is, U is open in the normal metric topology if and only if U is open in this d hat metric topology. Okay, then finally, let's say that this little L, which is going to be the set of, well, it's kind of a set of sequences of real numbers, where the absolute value of their sum converges. Then let's define d of xy to be the sum as n goes from 1 to infinity, the absolute value of xn minus yn, and let's show that this is a metric on our set L. And that's a good place to stop.